Okay, first thing we want to look at in terms of this whole idea of time being suspect, which really has to do with the relativity of simultaneity, whatever that means. We'll be getting into that. We're going to do a number of thought experiments here. And although normally I encourage you to take notes, I provide handouts with spaces for notes, and you can do the diagrams as I do them on the board. There are a lot of diagrams here. I don't want you to have to rewrite the same diagram over and over again. So I provided a handout with the diagrams on them so that you can take notes on the diagram in this case if you like, while we do it on the board so we can point out the key features and so on and so forth. So we're going to start off with diagram 1. And we're back to Alice and Bob here. And so we've got Alice's spaceship and Bob's spaceship. We haven't drawn them as spaceships. We'll imagine they're either spaceships or inside each spaceship. So these things here are clocks. Okay, so here's Alice's spaceship. Here's perhaps the front. Here's the back of the spaceship. And she has two clocks, one at the front and one at the back. They're synchronized, of course, in her frame of reference. Bob has a similar situation. He has his spaceship and Alice's spaceships are identical in terms of the same length. He also has two clocks, one at either end. They're synchronized with each other, so they read correctly, are always reading the same thing according to Bob. And at this instant in time here, everything is 0. So we're starting off with the clocks reading 0. In other words, time on Alice's clocks is 0, time on Bob's clock is 0. And then in the middle of each spaceship, the exact middle here, or we should say exactly between the two clocks, we have a little apparatus that can shoot out a light pulse in either direction. So it can shoot out a light pulse that direction and that direction at exactly the same time. And same thing for Bob down here. And so we have light pulses shot in opposite directions. They obviously travel at the speed of light, at speed c. And we just want to analyze what's going to happen here. Well, we have the clock set up so that when a light pulse reaches the clock, it sets a little trigger, takes a photograph, and records the time on that clock. Same thing for this clock and Bob's clocks as well. So here's our initial situation. Light pulses are shot in opposite directions. Alice and Bob are stationary in this first scenario that we're looking at. Nobody's moving. They're just sitting right next to each other. And they each do the experiment. The light pulses are set off at exactly the same time. So Alice's light pulses go off. Bob's light pulses go off at the same instant in time. And of course, we could verify that if we had a photographic clock right here in between them, such that they could take a picture and verify that, yes, they did go off at exactly the same instant in time because they're at the same location in space there. And just have to put a clock there that would indicate if they were shot exactly at the same time. So they're shot off. What happens next? So this is the first part of diagram 1. Let's imagine then that, carefully erase our light pulses here because they have now been shot off. And if we could imagine, we have one sort of about right there going that direction and right here going this direction. And same thing down here for Bob with our light pulses. In other words, they would track exactly, right? This light pulse would track with this one would track with that one. Assuming the light gun, as it were, is exactly in the center, we know the light pulses are going to reach the clocks on the ends at exactly the same time. So we'll draw that in here next. We'll assume, okay, they've actually reached the end here. This one has reached there. This one has reached there, and this one has reached there. Clearly, everything is symmetrical. Nobody's moving. The light clocks all trigger at the same time. So should have erased these zeros before, because obviously when they're midway going towards the clocks would no longer be a 0. They'd be at some value in between. So here we are. Then when they reach the clocks, we'll say, okay, this is time t sub a on that clock. And of course, since Alice's clocks are synchronized, it would be at time t sub a on that clock. And for Bob's clock, this would be time t sub b. And of course, over here on his clock, it would also be t sub b, assuming that the distances are equal in terms of the amount, the length traveled by each light pulse. So you'd say, well, what's the big deal? Really, there is no big deal at this point. We're just reminding ourselves what would happen if everybody was stationary at this point. Okay, that Alice would see her clocks trigger at TA. Bob would see his clocks trigger at TB. Everything is stationary. Everything is symmetrical. So TA would equal TB, and there'd be no problem at all. Nobody would worry about anything about their clocks being synchronized or whatever else. Okay, so that's that situation. This would also work if you just wanted to do paintballs, say, instead of light pulses. Obviously, the paintballs would not be traveling at speed c, but everything being stationary, one paintball going that way, one paintball going this way, one paintball going that way, one paintball going that way, they'd end up splattering on the clocks at exactly the same time, TA and TB. What we're going to do then in the next video clip is, and we're going to break this whole analysis into many more video clips than perhaps we've done in the past, just because we want to make haste slowly, as it were, not go too fast here, and also be able to look at each diagram carefully as we go along. So that's our first diagram 1. Again, perhaps not too surprising, not too weird or anything like that. Alice and Bob, stationary. We expect the clocks to be triggered at the same time, and everybody reads the same thing. So in our next one, though, we're actually going to put things in motion a little bit and then see what happens. We'll do a paintball example first, and then we'll come back to our light pulses.